There we go. Somebody else just came in. Shabnam? Shabnam, can you hear me? Hello?
Hi.
Hey, I just posted a link to a sign-in sheet. If you could just sign in real quick.
Okay.
And if you have anything specific, anybody that you came to this workshop for, just write it in chat. I'm going to go over several things. If there's something really specific you wanted to talk about, I can talk about it at the end if I'm not already going to talk about it. Okay. And let me know if you can see everything well enough on the board. All right, guys. So let me ask a general question here just to kind of gauge where we all are. If I said to you, what is the sine of pi over 6? Would you know what that is? Does anyone not know what that is? Okay. How about online? How do you guys feel about that? Does anyone know what that answer is? No, it's not 0. Hopefully everybody's in the right workshop because this is a review of trigonometry. So if you don't know trig, this won't be good because I'm not going to try to teach trig in an hour and a half. That would be neat. You're good. You're good. 1/2. Okay. So real quick, does anyone have any trouble with this piece? Pi over 6. What units is that in? Radians. I love it. Does anyone know what that is in degrees? Yeah. So, all right, let's talk about this since I have it up here. 0 degrees. What's this? 90. 180. 270. And then this is also 360 degrees, right? Okay. You with me? If I have a unit circle, and of course that's the big bad boy, right? Unit circle, pretend like that's a circle. We call it a unit circle because it has a radius of 1. Everybody with me so far? Pi over 2. Interesting. Yeah, that'll be what 90 is. Somebody remind me, do you guys remember what the circumference of a circle is, the formula? 2 pi r. So if r is 1, the circumference is 2 pi. So the actual distance, the physical distance around this circle is 2 pi. Which means 2 pi is the same distance, angular distance as 360 degrees. Is everybody sort of with me? I don't know, maybe. Okay. So which means if I divide by 2, pi is the same thing as 180 degrees. So this is pi. 360 is 2 pi radians. So like somebody said, 90 would be half of a pi. 270 would be 3/2 of a pi. All right, let me stop for a minute. Is that familiar to you guys? Is anybody blown away by this revelation? Let me know. Oh, there's Matt. Hey. Okay. All right. So I just want to gauge where everybody is. So let me ask another question and then we'll kind of launch into everything. So sine of pi over 6 would be 1/2, and we'll get into why that is true in a minute. So let's do this. Let's start from the very basic stuff. I just wanted to kind of throw some up here, see what you guys' reactions were. Let's see if this eraser works. Oh my God. Okay. What's the basic definition of sine? I'm given, let's do this, sine theta. Call this y, this x, and this is going to be the hypotenuse, right? So what's the basic definition of sine? Okay, good. All right. What do you guys know?
The opposite of.
Okay, I love it. Y over H, so it's going to be Y side over H. I love it. Right. So has any of you out there ever been taught SOHCAHTOA? Does that sound familiar to anybody? Anybody online? Is anybody out there? Hello. Okay, hopefully I'm still connected. We went over, okay. Okay, so real quick little personal rant. I hate this. That really does a disservice to people. It really does. If you understand that the sine is related to the y piece and the cosine is related to the x piece, makes so much more sense. So much in math, so much in science, so much in physics. Okay. SOHCAHTOA does a little bit of good for you. You can make jokes about Camp SOHCAHTOA and all that kind of business. But it is much more generally useful to realize sine is basically related to the y side, cosine is related to the x side. Okay, I like it. So all trig functions are ratios of sides of a right triangle. That's it. Okay. So what is tangent? So I'll accept two different ways to answer this question. Anybody? What's tangent? Sine is y over h. Cosine is x over h. What's tangent? Opposite over adjacent, otherwise known as y over x, which is also sine over cosine. Let me stop for a minute. Okay. All right, so let me see. Is everybody comfortable with what's happening at the moment? Anybody uncomfortable with this? Anybody not sure what's going on? I don't know what level everybody is at, so I just need to figure it out. Okay. All right. I think everybody's cool with this. What are the other three trig functions I haven't written up here yet? So we got sine, cosine, tangent. What am I missing? Inverse function. So not really inverse function. Be really careful. The reciprocal functions. What's the difference between a reciprocal function and an inverse function? Does anyone know? So real quick, go with me. Real quick side note: reciprocal versus inverse. Right? Just go with me for a second. All right, I know I'm a math guy. Got to talk about math. If I have a function f of x, let's say it's x minus 1. The reciprocal function will just be 1 over that. Reciprocal means flip, right? Reciprocating something just means flip. Somebody loves you and you reciprocate, you flip it back on them, right? You love them back. Aw. Inverse means the opposite. So the opposite of subtracting 1 is adding 1. Okay, just want to get that out there. Got to be careful. Are you guys all with me out there? All right, you're all very quiet. I'll work through that. Okay. So what I'm missing is the reciprocal of sine. What's the reciprocal of sine? What's the function? What's the trig function that's 1 over sine? No, again, okay. I love you, Michael. Arc sine is the inverse function. So we'll get to that in a bit. What's the reciprocal? What's 1 over sine defined to be? Does anyone know?
Cosine.
Cosecant. Yeah. So 1 over sine is cosecant. What's 1 over cosine?
Cosine.
1 over cosine. 1 over cosine is? Anybody? Well, it's not 1 over secant, it is just secant. And of course, this is the nice one. What's 1 over tangent? Cotangent. All right, let's stop for a minute. Okay. This is good to gauge where we all are. All right. So just to remind you guys, this is a trig review that leads really quickly into vector stuff. If you have a lot of trouble with what just happened on the board, you might want to come in for some help in the Math Study Center. If everybody wants to talk more about this, we can kind of convert this workshop into a more basic kind of trig workshop. That's fine. Let me see. Give me, everybody online, do this for me. If you're pretty comfortable with what just happened on the board, everything on the board, give me a thumbs up. Are you comfortable with the stuff on the board? Give me a thumbs up if you are. Nobody's comfortable. Nobody likes it. Okay, this is exciting. Okay. All right, let's try this. If you're uncomfortable with something on the board, give me a thumbs down or something. Or even just say it in the chat. I am uncomfortable. You are making me uncomfortable, Jeff. Okay, let's try this. If you can hear me, type something in chat. If you can hear me. Okay, somebody's comfortable. Shika can hear me. Ira, I think maybe, is Ira is comfortable. Shabana can hear me. Are you comfortable with what's happening, Shabana? Any questions on what just happened? You're comfortable. Okay, see, so what happened to you guys? When I ask you, I can't find the emoji. Oh, I see what you mean. Yeah, you can just type in chat, I'm good, right? The emojis are down where it says reactions. If you hit more and you can see reactions, there's the emojis and stuff and the little thumbs up. Okay, enough of that. Okay, so let's come back to this here. Let's see. So that's the basic definitions of trig functions. They are silly, simple. They are just ratios of sides of a right triangle. That's all they are. And then we can do all these crazy things with them, which is really neat. All right. So more than likely, depending on the teacher you have, some of you guys, it could be really, really important for you to know what this is. And some of you guys, not so much. So I don't know, depends. So let me do this. Let me really explain the idea and how to know what this is. Okay. I'm not going to prove the result. I'm going to give you a way to remember what this is. Okay. Somebody remind me, cosine likes what? Does it like X or does it like Y? What does cosine like? Cosine likes, and when I say likes, I'm just putting that in quotes. Cosine was, what's the definition of cosine again? What over what? What was the definition of cosine? Or better yet, X over hypotenuse, right? So that is the best way. It's cosine is the X piece. Cosine likes X. Sine likes Y. SOHCAHTOA doesn't say anything about that. So here's why that becomes crazy useful. Cosine likes it when it's close to the x-axis. So on the x-axis, do you see how right on the x-axis, is there any y component to what I just drew? Like if I was at this angle here, is there a y piece to that? Yes. Do you guys see that? Is there a y piece to this on the x-axis? No. So let's talk about sine for real quick. Sine will be easier to look at. Sine likes y. So at 0 degrees, sine of 0, in fact, let's do radians. Well, let's do degrees first, and then I'll talk about what radians is. Sine of 0 degrees is 0 because there's no y piece. The minute I build this up, let's say 30 degrees. Now there's a little bit of a y piece. Do you see how now there's a y piece to this situation, right? So now sine is going to build a little bit, and there's going to be a really cool pattern here in a minute. 1/2. Okay. at 45 degrees. Does anyone know what the sine of 45 degrees is? Yeah, I like it. Rad 2 over 2, rad 2 over 2, 11. So I want to go back and notice something. All right, sine of 0 is 0. Now stay with me. This is kind of cool. This is just something we notice. It's not something we can use to calculate, but it's just a noticing thing. It's just a pattern noticing. Isn't the square root of 0 still 0? Stay with me. This is going somewhere. What if I divide it by 2? Isn't that still 0? Right? What's the square root of 1? What's the square root of 1? 1, right? So do you notice square root of 0 over 2, square root of 1 over 2, square root of 2 over 2. So what should sine of 60 be? Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2. And then finally, I get this out of here. What's sine of 90 degrees? What's the pattern say it should be? Square root of 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. Well, what's the square root of 4? 2. And what's 2 divided by 2? 1. Of course, and that makes sense because sine likes y at 90 degrees. It's all y. There is no x. So, and again, nothing like you can use to calculate. This is just noticing an interesting pattern. Has anyone ever seen that before? The little pattern here? You guys doing all right? I'm a math teacher. I'm used to boring the hell out of people. Maybe that's what's happening. I don't know. Like, oh my God. Got to sit through this and get some extra credit. You guys okay out there? Give me a sign. You guys okay? Are you guys okay? My on ground people? Okay. But oh, look. People found it. All right, sweet. So I got 2 people paying attention. I love it. Okay. All right. So cosine, I really want this to make sense. As the angle increases, the y piece of the triangle increases. That's why this number keeps getting bigger and bigger and bigger until it's nothing but y. That's why it's 1 at 90 degrees. Cosine just does the opposite. Cosine starts at 1 and shrinks in the opposite direction until it's 0 here. Okay. Now, what's nice about memorizing the values in the first quadrant? If I wanted to know what the, what do you got, Jeff? What the cosine of 150 degrees is. What can I use so that it actually relates to something over here? What is this? Whoa, no. All kinds of things are happening. Okay, no. Okay. All right, I appreciate all the attempts. How big is this angle? What angle is all the way to here? What's this angle here? What's this? No, to here.
180.
180. So of course, what is this then? If that's 150, how much is here?
30.
30. Do you guys remember what this angle here is called? Starts with an R. No? Reference angle. So if I want to know what the cosine on 150 degrees is, now remember, you guys help me out. Stay with me now. Stay with me. And again, if I'm going too fast about something, say something. So what I like to say is if I'm going too fast, slow me down. If I'm going too slow, deal with it. So let me know if I'm going too fast through things, right? Okay. Cosine likes x, correct? Can anybody tell me, is x positive or negative back here? This is just a normal number line here, a normal XY plane. Is x positive or negative back here? It's negative, right? So cosine of 150 is going to be negative cosine of 30. Because this triangle is the same as this triangle. They're the same triangle. So however long this x piece is, this one's just as long, it's just negative. Okay, maybe. So that's why you only have to memorize stuff in the first quadrant, because everybody else is just a reference angle, and you just have to think, if it's sine is positive here, because the y is positive. Sine is negative here and here, because the y is negative. That's why it's so much better to know cosine likes x, sine likes y. All right, so Cotilla totally lets us down. Does one thing for us, and that's it. All right. Okay, maybe. This kills me. I can't see the reactions. And you guys are sort of poker face, but okay, you're not. Okay, I appreciate it. Okay. So that's some really basic stuff. So here's what I think. When I see this, here's what I think. Cosine likes x. 30 degrees is really close to x. So cosine should be relatively bigger. So it's rad 3/2. When it's close to the x-axis, cosine's big. When it gets further away from the x-axis, cosine gets small. It's that simple. That's a great way to memorize these. Okay, not sure where we are. All right. You guys doing okay out there? I keep asking that question because I can't see any of you. Okay, I got one thumbs up. I'm slowly losing people. Okay. All right. So that's some real basics of these things. Let's do something that's really applicable to science. Let me see. I sort of have an outline. Good. Okay. I love it. Yeah, we'll get there. Okay. Radians. The hell are radians? So real quick, how many degrees are there in a circle? All the way around the circle? You go all the way around, how many degrees? Why? Does anyone know why? Anyone want to know why? Anybody out there interested? Nobody wants to know? All right, I'll just turn off the audio. So it's only for the people. Are you guys out there? All right, I'm just going to stop trying. Okay. You guys let me know if you have any issues. Okay. It could have been anything. It could have been anything. We could have said there's 5,000 degrees in a circle. We could have said there's 2 degrees in a circle. Why did we choose 360? Because 360 is an easy number to break up. How many ways can you factor 360? A ton, right? You guys sort of with me? How many? It's actually kind of related to, well, what's our time based on? Isn't our time based on 60 seconds in a minute, 60 minutes in an hour? And again, why is that true? We just picked it. Didn't have to be that way. It's because 60 is a really nice number. So 360 is also a really nice number. Are you guys at all with me out there in here? You guys understand? It could have been any freaking thing. We just made that shit up. Degrees are completely made up. Okay. Radians aren't. Radians are an actual measurement. Can't make that shit up. So here's why it's called a radian even. Let me draw a better circle here. This is really important. So I got a nice circle. The circle's got a certain radius, right? If I were to take that radius, I take it, I've got it in my hand. I'm going to bend it. All right, take the radius, I'm going to bend it until it fits the circle. So I take that radius, here it is. Here's the radius. I bend it, and then I place it onto the circle. Right, there's the R. So I bent it so it fits right on the circle. The angle it goes through is 1 radian. We call it a radian because it's a number of radii, oh shit, or radiuses, if you want to be that way, that fits around the circle. Are you guys at all with me? Did any of you ever get taught that? Why we call it radian? We call it radian because it's the number of radii that fits along that angle. So if my radius is 10 feet and I walk 10 feet around the circle, I have gone through 1 radian's worth of an angle. Maybe. So watch this. This is kind of cool. What if I had a much smaller circle? You with me? This angle is still 1 radian. The same freaking angle is still 1 radian because the radius is much smaller. If I bend it, it goes exactly there. I really want this to make sense. No matter how big the circle is, 1 radian still means the same thing. It's still the same angle. Okay, maybe. Do you guys understand that radians are actual physical measurements, whereas degrees made up shit? So if I have an angle of pi over 6, that means if I walked around the circle, I would go this many radii. Pi over 6 radii worth of walking is what I would do. Maybe. So it's a physical measurement. We could also call this angle 30 degrees. Right? Because pi is 180, so pi divided by 6 is 30 degrees. It's just a name then. That's just a name that we give it. It's a 30-degree angle. Could have been anything. Okay, I want you guys to get this. So what does that have to do with anything? The preferred angle to use for trig, for any problems where there's angles, is radians, because that's an actual physical measurement. So real quick, let me see. So I don't know, I guess this is kind of cool. I love this idea, and it kills me when people aren't told why we call it a radius. It's a really cool idea to take the radius of the circle, walk that far, you've gone 1 radian. No matter how big the circle is, you will go through the same exact angle, right? Didn't this person walk further? But the radius is bigger. So they walk 1 radius. Okay. What did I just do? Oh, there it is. Oh, we already know that, don't we? To get all the way around, it was 2 pi radians, right? So it's 2 pi radians all the way around. And pi radians halfway. Pi radians is 180 degrees, right? Okay. Now again, real quick, guys, real quick. Can somebody please tell me, just tell me. If I have a circle with a radius of 7 feet, can somebody tell me what the circumference is? 14 pi. So 2 pi times 7, right? So if we walk all the way around, didn't we walk 2 pi 7s? 2 pi radii? Maybe, okay. So again, it's a physical measurement, radians. That's why it's more preferred. So for example, I can ask you what cosine of 45 degrees is, and it makes sense. Does anyone know what the cosine of 45 degrees is?
Sorry,
Rad 2 over 2. Okay. And I can ask you what cosine of pi over 4 is. Now pi over 4 equals 45 degrees. So that's also rad 2 over 2, right? You guys with me? Okay. But if I have a function, let me see if you guys, if I have a function like this, when I feed the cosine an angle, it gives me the ratio of sides of the right triangle that angle would live in. Let me say that again. When I feed a trig function an angle, it'll spit back to me the ratio of the sides of the right triangle that lives in. That's what trig functions do. Trig functions just give you ratios of sides of a right triangle. It's what they do. But, so I can give it anything. If I had a 45-degree angle and I named it Jeff, right? I'm a math guy. I'm weird as shit. So maybe I'll do that. Maybe I've got a little angle named Jeff that lives in my basement. And I say, what's the cosine of Jeff? Well, that's rad 2 over 2. So the cosine can handle any name you give to an angle. The problem comes in with this guy. He's on his own. He's out in the world. It's not inside of a trig function. So this has to be a real measurement, a real value. Because what could I call I could call the angle 45 degrees. I could call the angle Jeff. What the hell is Jeff times rad 2/2? I don't know. It has to be the only thing that's an actual physical measurement, which would be the radians. Okay, so I hope I've imparted to you why radians are so important and why physicists and scientists normally prefer radians, because it's a real physical measurement. Okay. All right. Okay. So let me see. Yeah, let's go back to that. So in the unit circle, if I'm at some angle, I've got my, let's say this is 1. This would be cosine, and this would be sine. So it doesn't, what fact about right triangles could I use to set up a relationship between these 3 things? This is a right triangle. So what do we know about a right triangle? What's true about the sides? How do they have to relate? What's the old Greek dude's name? Yes.
Pythagoras.
Yes. So it's the Pythagorean theorem. Good old Pythagoras. So it would be a squared plus b squared equals c squared. So that's the most basic trig identity, right? And then from that, you could create the other one. So if I divided this by sine squared, you would get 1 plus cotangent squared equals cosecant squared. You guys remember these? Hopefully you've done identities if you're taking a course that relies on trig. These could come up every now and again. Okay. All right. And then if I divide it by cosine squared instead, I would get tangent squared plus 1 equals secant squared. Okay. Does that sound familiar? All right. Okay. So those are some basic trig identities. These are called the Pythagorean identities, which makes sense because they came from the Pythagorean theorem. All right. Blah, blah, blah. Oh, quick thing I forgot about with radians and degrees. So hopefully that's nothing too amazing. Those are some basic trig identities. Quick thing about degrees and radians. So remember, pi radians was equal to how many degrees? 180. So if I want to convert, let's say I've got 15 degrees and I want to know how many radians that is. One thing you can use is an old standby conversion trick. Right? What unit do we not want anymore? If I want to get here. Do you want to have degrees there still? No. So I want to kill the degree. So I put it down here so it cancels. And up here I put radians. Pi radians is 180 degrees. Divide. Yeah. 15 divided by 180 is 12, I think. So it'd be pi over 12. Yeah, makes sense. So pi over 12 is radians. Okay. All right. So that shouldn't be a big mystery. I think do most of you guys know how to convert between radians and degrees? I don't know why I keep looking to the online. They've stopped talking to me entirely. Okay. You guys still out there? Anybody? Is anybody out there? Okay. Yes. Alberta. Okay, thank you. Chica still on. Okay, good. All right. So that's just the basic conversion between, so if I had 34 radians and I want to convert that to degrees, well, I want to kill radians this time. So then I put pi rad 180 degrees. So then 34 times 180 divided by pi. And that would be the number of degrees. All right. So a lot of conversions work this way. This little grid is really awesome. Way to convert a lot of different things. Okay. I like it. So, all right. So if there's no other specific questions about just trig by itself, I'm going to get into vectors kind of stuff. Does anyone want to talk about vectors? Anybody need to talk about, do you need to talk about vectors? Uh-oh, looking at the clock. It's okay. Anybody? Yes? Okay. Yes. Okay. Okay. Maybe that's what you guys have been waiting for. All right. Okay. So one of the most basic thing about vectors. So can somebody tell me what are the two things that a vector needs to be fully defined? What do you need to know about a vector for it to be fully defined? There's two things. Magnitude is one, and direction, 11. So magnitude and direction. I like it. So let's say I've got, somebody's got a force of 10 newtons, right? Acting at an angle of 40 degrees. So there's magnitude and direction. Is everybody with me? So maybe this is somebody pulling a box, right? You've probably seen a lot of pictures like this in particular physics. Okay. Can somebody tell me what is the force that's acting in just the x direction? What is the force that's going this way? Because if I pull it with a rope, can you guys imagine a rope at 40 degrees and I'm pulling this thing? Which direction will it go? Well, it's on the floor more than likely, so it's going to go that way. But I really want you guys to get this. There is a up component to my force, and there is a side to side component to my force. So here comes a little bit of trick. All right, so this is obviously a right angle because this is x, this is y. Can somebody tell me the x component of the force? Can somebody figure that out? How would you get? Now, we're not going to do friction. We're not doing friction yet. Friction's a whole different deal. But it would just be a force that's acting. So in the force of friction would just be acting negative x, right? But let's say this is a freshly waxed floor. There's basically zero friction, right? Can somebody tell me what the x component of this force would be? What trig function relates this side and this side? Cosine, 11. So what's the cosine of 40 degrees? Don't tell me what the number is. Just tell me from the triangle. Cosine is the x side divided by the hypotenuse. Can you solve that for fx? Can you solve that for the x piece of the force? What would you do to solve that for fx? How would you solve that? Yeah, you would multiply both sides by 10, right? Bam. So the x piece of the force is 10 cosine 40 degrees. Does anyone have their calculator? Can you tell me roughly what that is? I think it's roughly going to be 6.7, maybe? Does anyone get a calculator? No? All right. Let's see, did I bring a calculator? No. Okay. So mine is recharging. Yes. Nobody's got a calculator. Okay, okay. So I think this is roughly, just kind of guessing here, 6.7 or something. Nobody, 6.6. That's pretty close. Okay. 6.6 newtons. That's rounded quite a bit, right? Okay. Can somebody tell me? Oh, somebody's got it. 6.669. Is that what you got? So like 6.7 if you're rounded. Okay. Now you guys, real quick, you guys, what's Fy? I want you to realize something. This is so cool. Cosine likes x. So what's the x component of this force? It's the force times cosine of 40 degrees. So what's the y component of the force? The full force times sine 45 degrees. I'm sorry, 40 degrees. And I think that's going to be maybe 5 point something. 5 point, I don't know, 5.8. Or wait a minute. Maybe 6 point something still. 6, I'll say. Of course, I'm trying to do some weird ass trick in my head. So maybe 6.2. I don't know. Really? No, that can't be right. No. It's got to be less than 6.7. Yeah, 6.4 sounds about right. How did I know that? Because doesn't cosine get bigger the closer it is to the x-axis? Isn't 40 degrees closer to the x than the y? So the cosine piece should be bigger than the sine piece. Does that make sense? Because 40 degrees is a little closer to the x. Does that make sense? Are you guys used to breaking vectors up into their components? Have you guys been doing that at all? It's basically what we just did, right? Okay, so here's what's really cool. Okay, this is not a true statement, but it is a nifty way to remember things. If I know the full magnitude of the vector, could be a force vector, a velocity vector, whatever, right? To get the y piece, the sine is sort of like a percentage of the full amount that lies in the y direction. So if I take 10 times sine of the angle, I get the piece in the y direction. If I take 10 times the cosine of the angle, I get the piece that lies in the x direction. So this component, this much force, is lifting the box up. Now, real quick physics question. If I have a piece of my force lifting the box up, what force am I decreasing? I don't know. This is a more just pure physics question. Part of my force is going into lifting the box up a little bit, correct? You could do this. What's the name of the force that counteracts weight? Starts with an N. You guys know that yet? The normal force? Has anybody ever heard the normal force? Okay, I don't know how much you guys have done. Somebody said friction earlier, so I was hoping you guys, okay, not yet. I'm sorry. It'll come. Okay. But you guys are doing a little bit with vectors, correct? You guys are doing a little bit with vectors. Okay. Okay. Well, so this is just one vector, and we broke it up into parts. That's pretty straightforward. So let me ask you this question. If I have a box, let's say we are floating above this box. So that box is on the ground, right? You guys with me? This is an aerial view. We're floating above the box now, right? Let's say somebody pulls it this way, right? Say that's north, so this is just north, east, west, south. What direction will it move? North, holy shit. Now, what if at the same time somebody's pulling it this way with a force of 5 newtons? Will it still go straight north? it'll go roughly northeast, not perfectly northeast, will it? It won't go perfectly northeast. It'll go more, yes, good. It'll go more north than east. Why? Because there's more force that way. Okay. I like it. So a different kind of question that you could be asked is, what's the resultant of a series of vectors acting on something? So in this case, force vectors. So how do I find the resultant force vector? We already know it should be moving in this kind of direction. So what is the resultant force vector? So we said earlier, what two things do we need to identify a vector? Two things. Magnitude and direction. So magnitude, a number normally, direction is going to be an angle. Okay, so watch this. This is kind of cool. The one we just did was I was given a force and we broke it up into its parts, right? The Fx and the Fy. So what we're about to do is we're about to recombine these. This is an Fy and this is an Fx. I want to recombine them into one vector. I don't really have this drawn sort of to scale. Let me make this a little bit better, because the length of the vector represents the strength of the vector very often. So watch this. I don't know if you guys have done this before. If I kind of finish this, I make a little triangle here, right? So this is 5 and this is 9. How do you figure out this length here? That'll be the magnitude of the vector. How do you figure out that length? This is 5. This is 9. How do you figure out this length? What do you use? Pythagorean theorem, 11. So the magnitude would equal the square root of a squared plus b squared, right? So 25 plus 81. So I get the square root of 106, whatever that is. Okay, so that would be square root of 106 newtons, because this is a force. Now, how would you figure out the angle that that's acting at? What trig function would relate these two things? Anybody? What trig function would relate these two sides with this angle? Tangent, yes, right? So from the picture, tangent theta is the y piece over the x piece. So I would just have to do, how do I solve this? What would I have to do to both sides to get rid of this tangent? What do I have to apply to both sides? Now you can come in with what you're trying to do earlier. Not the reciprocal. Now you actually do want to use the inverse. You want to use the arctangent, which we represent like this very often. Your teacher might want to write the whole arctan. I don't know, it's up to your teacher, right? And that you can just do in your calculator. Are you guys with me? By the way, one thing about your calculators. Do you know how to change from radians to degrees and degrees to radians? You have to be really careful that you're in the right mode, right? So let's say I want this in degrees. Can anyone tell me what that is in degrees, that answer? Anybody? Dude, somebody out there's got a calculator with inverse with trigonometry on it, I believe. Oh, okay. 60.95 roughly. I like it, which makes sense because it's definitely going to be more than 45 degrees. So 60.9, that makes sense. It's going to be more north than east, like somebody said earlier. Somebody good so far. I mean, this is just combining two vectors, that one's fully X and one's fully Y, right? Okay, all right. Okay, so combining two vectors is sort of the opposite of breaking a vector down into its parts, right? It's really just the opposite of that. So what if, let me see if you guys have ever had a question like this. Let me throw a question up here. Let's say there's an airplane. Actually, let me do this. Let's start off easy. So I'm going to start off easy. Like when I say easy, I mean actually easy. Let's say there's an airplane. Let's see, what do I want to do? Sure. That's going 100 kilometers per hour straight east. And there's wind going at 25 kilometers per hour east. Yes? How fast is the plane going to go relative to the ground? So somebody's standing on the ground, looking up at this plane. Yes, that's a plane. This is the easy one. So how fast is that plane going overall? There's a wind going 25 kilometers per hour east. The plane is flying 100 kilometers an hour east. So how fast is that plane going relative to the ground? Yeah, 125. You just add these two. Why do you add them? Because they're both acting in the same direction, right? You just have to straight up add them. They're both X components. So you can add them directly. So this will be 125 kilometers per hour, according to the guy on the ground. Now, here's a much harder problem. Let's say I've still got this plane going, and let's let this thing, yeah, sure. Let's make it 500 kilometers per hour east, right? So it's going 500 kilometers per hour east. And there's a wind coming at, let's see how I want to describe this. 20 degrees like this. There's a wind coming 20 degrees south of east at 80 kilometers per hour. Yeah, I think. Yeah, I could have made it more interesting, but that's okay. I'll just build up to it. Is this as easy to combine the two vectors? Why is this one more difficult to combine the two vectors? Yeah, different directions. I love it. But, hey, go ahead. Yeah. So this vector here has a y piece that I could put together with this. And then it's got an x piece. So what you do, if you have a bunch of different vectors acting on something, like a bunch of different forces, a bunch of different whatever it is, you break everything down into x and y pieces, and you combine your x pieces, combine your y pieces, right? So how do I break this thing down? What would the, let's call this the velocity vector. So I want the velocity in the x direction, and I want the velocity in the y direction. Can somebody tell me what the velocity in the x direction is going to be? Anybody? It's just like the problem we did earlier. Yeah. Times 8. That's all. 80 cosine 20. It's kind of nice. If I know the full thing and I know the base angle, the x piece will be cosine times this, and the y piece will be sine. So I'm going to have to ask you for some help again. 80 times cosine of 20. I don't know. Do I want to try to guess that? about, I don't know. Let's see, maybe 70 or 60. I don't know. Somebody's got a, let me know, who's got a calculator out there? 80 times cosine of 20 degrees. $75. Okay, sounds about right to me. Not degrees. 75.175 kilometers per hour. And what about 80 times sine of 20? $27 point, oh, I get two different answers, neato. 27, so is it 27.4 maybe? So here's how this works. If you want to see, so here's the plane flying 500 kilometers an hour. And then if I put the wind, it's going at 80 kilometers per hour at a 20-degree angle. I want to know what this resultant is here. So now, if I take, okay, if I take, this is acting in the X direction. So what is all the stuff that's acting in the X direction? 500 and 75.175. So in the X direction, I get 575.175. That's what I get in the X direction. What's acting in the Y direction? I might be too far off the chart here now. Can you guys still see that? What's acting in the Y direction? What's the only thing acting in the Y direction? Hey. Are you here for the trig workshop? Oh, okay. We've moved on to vectors. Vy, sure. So that's this guy. So 27.4. Yeah. 27.4 kilometers per hour. So now I've got, in the X direction, I've got 575.175. In the Y direction, I've got 27.4. Well, that's not really to scale. So now I just want to know what this resultant is. So if you have multiple vectors acting on something, you break each vector down into its X, Y components, and then you just put the X's together, put the Y's together. It's almost too nice to believe because they're acting in the same direction. They will actually affect each other. So now I can just do what we did earlier. I can just do Pythagorean theorem to figure out what this is, right? So it'll be 575.175 squared plus 27.4 squared, square rooted. Whatever that is. That's good old Pythagorean theorem. And who remembers, how do I get the angle this is actually traveling at? What trig function relates these two sides here? Second, tangent. So I take the arc tangent of y over x, 27.4 over 575.175. So whatever those are. So there should have been some kind of problems that sound very familiar to this. I don't know. Have you guys done this kind of problem before with the vectors? Have you guys done this kind of problem before? Okay. Sort of go a little insane when I don't get any replies. Okay. I mean, you got here right in time. So I pretty much finished everything I was going to say. Do we want to go back? Because the last time I did this, and I can put this video out there because I had a little more participation last time I did. So there's I did it on Zoom a couple years ago. And when I got to the end of what I had kind of prepared, I just opened it up to anything specific that people were hoping we talk about. And one thing that came up is they wanted to go back and talk more about some basic trig stuff. So the floor is sort of open, right? So you came in, you kind of missed the trig stuff. We talked a little bit about unit circle, what are radians, how to convert between radians, degrees, all this kind of stuff. Is there anything you came hoping we would talk about that we didn't talk about? Or anything you wanted to get that you now can ask about?
I would ask for like unit circle stuff.
Unit circle stuff. All right. Let me see.
Or just need like a.
So let's see. What you missed earlier was the idea that cosine likes x, sine likes y. Cosine likes x. It's hard to say that. Sine likes y. Right, so it's much better than SOHCAHTOA. SOHCAHTOA is out there. People know SOHCAHTOA. SOHCAHTOA doesn't really help you that much. And as you can see from the vectors we were doing, if you remember cosine likes x, and you're trying to get an x component of something, cosine, as long as the angle is in the base, you're gold, right? You don't need SOHCAHTOA. So that's why, for example, since sine likes y, at 0 degrees, there is no y. It's all x. That's why sine of 0 is 0. The minute I lift off of there and get up to like 30, do you see how there's a y piece now? And it's not very big, but it's certainly bigger than it was. So now it's at 1/2. If I go up a little more, it's going to grow a little bit more. And at this point, I pointed something out. So does all this sound vaguely familiar? Notice this. This is cool. What's the square root of 0? Divided by 2 is still. All right. What's the square root of 1? So that's the same thing, yes? Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2. So what should the next thing be? Square root of 3 over 2. And that's what it is, right? And what should the next thing be? What should it be? No, come on. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. What's the square root of 4? 2 divided by 2 is 1. So why does that make sense? Because again, sine likes y. Do you see how sine measures how big the y piece is? And when it gets here, it's all freaking y. That's why the whole the whole radius is y now. Okay, I like it. Does that make sense? That's it. And again, you see, as I move, don't I make these little triangles? Isn't trig based on triangles? That's why trig in the unit circle makes sense, because as you move, you make these little triangles. Now, okay, you're welcome. This is the same thing I said earlier, but I don't know, you might have come in after I started. So cosine just does the exact thing in the opposite way. So cosine would start at 1 and then shrink by this, because it's all x. Then this triangle, it's a little less x, and this triangle is a little less x, until here, there's no x. It's all y. Do you now understand why I don't like SOHCAHTOA? You ever heard of SOHCAHTOA? All right. It seems all nice and good. It's all like, keep SOHCAHTOA and all this kind of crap, but it just doesn't do much for us. Okay. Let me see. And then, of course, we talked a little bit about reference angles, how you only have to memorize the first quadrant because sine is going to be positive where y is positive. So sine is negative down here. Cosine is going to be negative when x is negative. So it's negative here, right? Because cosine likes x, sine likes y. Makes everything make a lot more sense, or at least in my opinion. So again, if I had to figure out what the sine of what, Jeff? 300 degrees is that going to be negative or positive? Sine likes y, and y is negative there, right? So it's going to be negative. And what is the actual angle in the triangle that I would be curious about? What is that angle? How short of 360 did we make it? What's left over here? What's this? 60. So that's the reference angle. And we use reference angles because they actually live in the triangle we would want to talk about. So that's why this is equal to negative sine 60. So if I have this from the first quadrant memorized, I can do anything that's 60 degrees away from the x-axis. So what's sine of 60? Here's what I think. You ready? Here's what I think. I don't have this shit memorized. Sine likes y. 60 degrees is close to y. It's going to be the bigger option. It's rad 3 over 2. That's exactly what I think, right? Sine likes y. The closer it is to y, the bigger sine is. The further away from y it is, the smaller sine is. And cosine just the other way. How's that? Maybe? Okay. What else we want to talk about? You guys have any other leftover questions you wish I would have addressed that you just didn't ask yet for some reason, or anything else? Anything you think you missed you want me to go over again? Let me think. Talked about what radians mean, why they're better. Let's see. So the reason radians are better is because we completely made up 360 degrees. Completely made it up. We could have made it 5,000 degrees. It doesn't matter. We just decided to break it into 360 parts. Couldn't we have broken this into 400 parts? And then it would have been 400 degrees, right? So the better unit to use is the one that's built from measurement. So if I take this radius and I bend it and put it on the circle, the angle I just went through is 1 radian because it comes from 1 radius length along the circle. So 2 radians just means I walk 2 radius worth. So if the radius is 10 feet, if I walk 20 feet around the circle, I just went through an angle of 2 radians. So radians are an actual physical measurement, which is why they are preferred. Okay, maybe. I feel like I have somebody who came in who wasn't here earlier, so I'm just seeing what he wants. But if anybody else has anything else you were hoping to God I was going to talk about, I don't see anything specific from you guys. So you just kind of came and you just were like, I'm going to take whatever the hell this guy gives me. Came for the vectors. Glad I got some trigger. Is there anything about vectors that I didn't talk about that you were hoping I would? I mean, we sort of did just a few vector questions, but I wasn't getting a lot of feedback. So anything about vectors I didn't hit that? Yes. Tangent and secant? Oh, the relationship. Well, so we know this is true, right? Is that cool? Yeah, that's the basic. The sine piece is the y and the cosine is the x. So sine squared plus cosine squared must be the radius, which in the unit circle is 1. Okay. If you divide these by cosine squared, what do you get? What is sine over cosine? Tangent. Cosine squared divided by cosine squared. 1 over cosine. So there's one relationship between tangent and secant, right? I'm not sure what you mean otherwise, because tangent is sine over cosine. Secant is 1 over cosine, right? So I mean, the secant is tangent divided by sine. There's another.
Mostly said this because of the quiz we took yesterday, which was on that trigonometry, kind of was like the volume.
Oh, you're from my, okay. That's why you look familiar. I don't know. I see people and I don't know if they know them from the Math Study Center or, okay. I got you. How did you find out about this workshop?
My physics.
Oh, because you're in a science class. I got you. Okay. Yeah, so this is the basic one way to see a relationship between tangent and secant. It's just by that Pythagorean identity. I like that. So Alberto says, I came for the vectors. Okay. So Alberto, you're cool. Did you need anything else about vectors? Alberto, are you good? Think you're good? Anybody else? I mean, we could do another, if you have a specific problem, if you have a type of thing. Otherwise, I'm out, right? I said everything I was gonna say. Okay. All right. So it feels like most of you guys just came just to get what you could. And again, if you had something you wish I would have talked about, just let me know. Otherwise, you guys have anything else you wanted to ask? Yes, I will. Yeah, so I'm recording right now, so I'll put it up on the YouTube channel, so you'll be able to see it, yeah, just like any other thing. So there's another one, math review for sciences, that I did yesterday. So that's up there right now. So this one will be up there, hopefully tonight. YouTube channels. I'm gonna email that to your professors, but my YouTube name is Waller is me. So if you just go to YouTube and search for Waller is me, you'll get all my videos. If you look in reverse chronological order, this one should be up there tonight. Yeah, I don't know how good this was because I just sort of like plowed through. I really live off of interactions. So I think you guys mostly just came to absorb whatever I had to throw at you. So I just kind of went through it. If everybody's cool, if you have nothing specific else you needed, we're gonna head out, which is fine by me because it's been a long day. So you guys good here? Yeah. All right, guys. Well, did everybody sign in that's online right now? Oh yeah. Put your physics professor down a second. Yeah. Uh-oh, Alberta did not. Okay, Alberta, give me just a second. Let me put that link up here. Oh, geez, it's way back here. Wee, there it is. Okay. So Alberto, just take a second and fill out that form. The link's up there. Okay, otherwise, that's it. Thanks for coming, and hopefully it was useful. And I'll put the video up, and I'll also include a link to the one I did that was on Zoom. That one I had nothing on, and nothing against you guys. It's fine that you came, you just wanted to get what you could. But there's a little more interaction, so I sort of built off of that. But so they'll have both of those in the email to your instructors, so they should send that to you. Okay, so thanks for coming, and you actually can come into the Math Study Center if you have questions. There are several tutors who could help with physics. I could help with physics. There's a few other tutors that can help with physics. If you have some chemistry, there's a few that can help with chemistry. We can help with the math that you're working on. So feel free to come in for that. Okay. All right. Take care. Have a good weekend. You're welcome. Bye, guys.